We have seen how the Carnot engine works or Carnot cycle works. Now, we are going to discuss about some other types of engines, some of which are realistic engines. So, among them today we are going to talk about Stirling engine, gasoline engine and diesel engine. We know that we have already talked about that the steam engine and Stirling engines are external combustion engines, whereas gasoline engine and diesel engines are internal combustion engines, and we know that there are petrol cars and diesel cars, right. So, in petrol cars typically gasoline engine works, and whereas in diesel cars the diesel engine works. So, we are going to talk about those things today. Those are realistic engines, and we will see an equivalent ideal version of those realistic engines. But we will start first with Stirling engine, because that is something which is which has very similar efficiency and works in a similar manner as Carnot engine. However, unlike Carnot engine, it is actually a realistic one, and we are going to show that today. So, here we are showing a the Stirling engine cycle for an ideal system, assuming that there is no losses due to frictions and any other things. How does this particular ideal Stirling engine works? So, it is very important, interesting to know that the Stirling engine came almost 8 years before the Carnot engine, around 1816, whereas the Carnot cycle or Carnot proposed the Carnot cycle around 1824. So, even 8 years before that, Stirling made an workable engine. Now, the reason was that there was a steam engine before. Steam engine came around 1760s, and there was a lot of explosions in the steam engines. So, in order to reduce that explosions, he came up with Robert Stirling, who is a priest, came up with this particular design of Stirling engine, and it has a lot of advantages. We are going to talk about that today. So, an ideal Stirling engine basically has two pistons. So, one is right side piston, another is like left side piston, which is connected through something called regenerator R. One of the piston is in contact with high temperature heat bath or reservoir, and another piston is in contact with the low temperature reservoir. So, it starts with, let us say, at the point 1, where there is a change in the volume of the right side piston, the gas in the right, and this is filled up with some gas, hydrogen or helium. So, in the right side, first the compression happens, where the volume decreases in an isothermal manner from 1 to 2, it is shown here, and during that process heat gets released out of the system, and then it comes to the point 2, where now the gas is in contact with the high temperature reservoir. So, earlier the gas mostly was in contact with the low temperature reservoir, and it got shrunk in an isothermal manner, releasing the heat, and then once it shrank, in the second step the gas which is in contact with the high temperature reservoir gets the heat from the regenerator which is inside the system, but there is a shrinking of volume on the right hand side, and there is an increase in the volume of the left hand side piston. So, by that there is no change in volume. In the third step, which is here, this is the power piston, where there is an expansion in an isothermal manner from 3 to 4, where you can see that the gas which is in contact with the high temperature reservoir expands, whereas the low temperature reservoir it is same, there is no change in that. And in the last step there is a decrease in the volume. Since there is a decrease in this side and increase in this side, the volume remains constant. Now, see that in these 4 steps, in 1 to 2 there is an isothermal compression, therefore, heat goes out of the system, and in 3 to 4 there is an isothermal expansion. So, the system takes heat from outside. However, in the other 2 steps from 2 to 3 and 4 to 1, this is 2 to 3 is actually a isochoric process. Ideally, this isochoric process would require a lot of thermal reservoirs in order for it to be reversible, because the temperature is changing at each step of the way. So, in order to make it reversible, it has to be attached to several infinite number of thermal reservoirs at different temperatures. However, an ideal Stirling engine is designed such a way that the 2 to 3 the heat is taken from the regenerator. So, the QR which is taken here, that is the heat taken from the regenerator, which is this one, and in this step the heat is released to the regenerator between 4 to 1, and regenerator is typically a wire mesh and therefore, it can absorb the heat and release the heat. So, this QR the same amount of heat between this 2 to 3 and 3 to 4 is done within the system itself. So, therefore, no heat is taken or given out in this particular 2 steps. This makes the efficiency of the engine, which I am going to talk about, is almost exactly like Carnot engine, because it works within the 2 temperature reservoirs, one is the TH and TL, and we are going to show that the efficiency becomes exactly like Carnot engine if there is a regenerator here. If there were no regenerator here, then what would happen is that the heat has to be taken from outside, and therefore, the efficiency will be reduced, because then it will no longer be a Carnot engine. So, we are going to calculate the efficiency of the Stirling engine. So, this is a PV diagram. This is an isothermal step, isochoric step, isothermal and isochoric 1, 2, 3 and 4. So, 1 to 2 is an isothermal compression process, and we know that in isothermal compression process delta U equal to 0 and Q equal to minus W, which is nothing but nR T L ln V2 by V1. In the 2 to 3 step, it is actually a isochoric process. So, in an isochoric process, the heat we call that first one as Q1, which is the heat that goes out of the system, and this is an isochoric process is QR, which is CV. So, QR will be CV because it is in constant volume process, TH minus TL. 3 to 4 is isothermal expansion, again let us call it Q3. Oh, this is the place where the heat will go inside the system. Q3 equal to nRTH ln V4 by V3, and 4 to 1 will be again QR CV TL minus TH. So, you see that in the second to third step, the amount of heat is exactly the same as, but negative in sign as 4 to 1. So, they will exactly cancel each other if that is taken from within the system itself, and regenerator is part of the system itself. So, although we the system takes heat here and rejects heat in this particular step, nothing is coming out of the system. So, if I calculate the efficiency with the regenerator, then the total change in heat is Q1 plus Q3, and heat input is coming only in the 3 to 4 step, which is Q3, which will be 1 plus Q1 by Q3. That means 1 plus, now Q1 is nRTL ln V2 by V1, Q3 is nRTH ln V4 by V3, nR cancels each other, 1 plus TL by TH, and we know that V2 equal to V3 and V1 equal to V4. So, therefore, V2 by V1 is equal to V3 by V4, and therefore, ln V2 by V1 equal to ln V3 by V4 equal to minus ln V4 by V3. So, therefore, there will be, so we can exactly write that minus ln V4 by V3 by ln V4 by V3 cancels, and we get 1 minus TL by TH. So, this is an engine which between it works between two temperature reservoir TL and TH, and it has exactly same efficiency as that of the Carnot engine. So, this is a realistic example of a Carnot engine which came interestingly even before Carnot proposed the engine itself. Now, you see that if this the regenerator would not be there, then your efficiency would be that Q1 plus Q3 is the total work done divided by the heat input that is there in the Q3 step plus QR, because in this step also heat has to be taken in and in this step also, and therefore, because the other two heat processes Q1 and minus QR will cancel in the numerator, and therefore, this will have lesser efficiency. Let us call it like efficiency of a irreversible Stirling engine, which will have lesser efficiency than a reversible Stirling engine. Okay. So, now we are going to show you a realistic Stirling engine, which however has instead of two pistons like this shown here, it has only one piston, and this is the typically Stirling engine model that are sold, and we have also one of that with us. We are going to show you that. So, but before we are going to show you that, I am going to explain that with the help of a picture. So, the Stirling engine typically has a few important components. So, this is an example of a Stirling engine model. As you can see, there is only one piston here, and there is a displacer which is of made of foam, which is here inside. The whole thing is sealed, there is a gas inside this system, and you can look at here is that. So, this is the piston that I have drawn. One most important thing is two cranks, one is here crankshaft and another is here, and you can see that they are 90° apart. Right now this is down here just like in this configuration number 1, and this is perpendicular to the other one, which is like this. I have joined the two in order to denote that they are connected. If this one rotates, the other one will also rotate. Right now the volume is some midway. As you can see, there is small gap between the white colored thing and the bottom, there is some gap. So, this is in the midway situation and the displacer is down. Now, what is going to happen is that the Stirling engine works, as I said, based on temperature differences. The temperature difference can be created by putting heat or high temperature in the lower plate and low temperature in the upper plate, or the other way around, low temperature and then lower plate and high temperature in the upper plate. So, basically you have to create a temperature difference. The temperature difference can be either side. Now, but we have shown here the picture in order to mimic something where the temperature is coming from the bottom. For example, right now the displacer is down and the piston is midway. Now, once the system gets heated up here, now what will happen is that the most of the gas is in contact with the low temperature. So, therefore, what is going to happen is that it is going to shrink. So, this is the way. So, from your side it is clockwise. So, it is going to shrink. So, in the second step, as you can see here, and once it shrinks the volume, the displacer comes in the middle, as you can see in the picture and you can see in my model also. Next step, what is going to happen is that now the gas is in contact, some of the gas is in contact with the hot plate. So, therefore, it is going to take in the heat, and keeping the same volume, the pressure is going to increase, which will push it further, and in the next step the displacer is going to go to the top, piston is again going to come in the middle. Now, in this step, now most of the gas is in contact with the hot plate. So, therefore, it is going to expand now. Once it expands, you can see the piston has moved up. So, this is the power part of the whole cycle. So, this is an isothermal expansion that is going to happen, and which again will move So, now movement of the piston is actually moving this particular crankshaft arrangement, and this is again connected with the displacer. So, the movement of the piston causes the wheel to rotate, which in turn causes the displacer to also change at the same time. So, the displacer is changing because the piston is going up and down, that is first important thing. And secondly, the power part of the piston where it actually pushes up and let us say rotate helps helps to create the momentum, which in turn goes makes the complete cycle. And we can we have shown here that the PV diagram looks like an ellipsoid, where 1 to 2 is the step of isothermal compression, and then 2 to 3 is like a constant volume process almost, and then 3 to 4 expansion will happen, and 4 to 1 is again the constant volume changes, but it is not an ideal engine. So, therefore, it is exactly not like exactly a constant volume thing. Okay. So, now we are going to show you that we are going to put it on a hot water below, and we are going to show you that from your side it is going to rotate in this direction. Okay. So, let us do that. You see from your side the piston is on my side. So, the way we have put it, the piston is on my side, and in that case it is going to rotate in the clockwise direction. So, before we show you that, we are going to also calculate also measure the temperature of the two plates. It is fluctuating between 24, 27, things like that. Let us see the bottom plate. Bottom plate is already a little bit higher, 27.3. Now, let us put the hot water. We have hot water here. Temperature of the water is 70.7 degree. Now, we are going to put the plate. Remember, I told you the piston will be opposite from your direction, and in that case it should rotate clockwise. So, right now this plate is going to get heated up, this is going to be cooler. So, compression is going to happen first, and then middle, and then expansion will happen. Yeah, it started. It is going to pick up the momentum as the plate gets hotter and hotter. Let it be there a little bit time. So, you see, unless there will be this 90-degree arrangement, once this expansion will happen, it will just get stopped, because in that case all the gas will be in the bottom only and the piston will be expanded form. But just because the piston and the displacer are in a 90-degree shift arrangement, so I can show you that while this video is playing, that in the first stage what is going to happen, what is happening is that, now let us look at from this angle. Now, in this angle the piston is in the middle and the displacer in the down place. So, this is the place of the displacer, this is the piston place, and they are connected together. Now, what is happening in the next step is that, since it is getting cooled down, this is the number 1. In the second phase, second step, piston gets lower and displacer goes to the middle. So, this is connected to the displacer, this is connected to the piston, this is connected to the displacer, connected to the piston. Now, you see there is a clockwise rotation happens. In the third step, piston again goes to the middle, but displacer now goes to the top, and in the last step, now displacer goes to the middle again and piston goes to the top. So, and that is the reason that whenever the piston goes up, because of the displacer, displacer helps the air to be connected, to come in contact with the hot and cold air. So, that is a very important part of the displacer. Another important aspect of the displacer is that it absorbs heat and gives away heat during the phase where there is a constant volume changes happens. Okay. So, now if I change the hot and cold side, what is going to happen? So, you see if I start with 1, so right now when the hot side is here and cold side is here, then it is going on in according to this diagram going on in a clockwise manner. Of course, that corresponds to this movement, but let us say this side is colder, let us say this side is colder and that side is hotter. So, what will happen is that if this side is hotter, the upside is hotter, so then it will expand. So, that means from 1 it will directly go to 4. So, you see once that happens from 1 to 2 to 3 to 4, this rotation is in clockwise direction, this one to this one to this one in clockwise direction. But if it goes in opposite direction 1 4, then it will rotate in the other direction. See right now it is this thing is rotating in a clockwise manner, but if this is colder and this is hotter, then what is going to happen is that next step from 1 it will go to 4, expansion will happen. So, 1 to 4 is an anti-clockwise movement for this guy. So, it is going to rotate in the opposite direction. So, right now from your side when the piston is away from you, it is rotating in clockwise, but if I put it in front on top of ice, it is now going to rotate in the anti-clockwise direction. So, we are going to show you that. And also one important thing is that if the flywheel is not heavy, then also this rotation will not be possible, because you need to have enough momentum for it to go over one cycle. So, there is an expansion phase that happens, right, that gives a certain rotations of the wheel, but in that if you have enough momentum, then you can cross over the next part of the cycle, and that is why you need some momentum on that. Now, we are going to put it on the ice. It is already slowed down. Now, you saw that there was a clockwise rotation you have seen. Now, you see now it is going to have anti-clockwise rotation. I am going to give you a clockwise rotation just to see whether it happens or not, but it is not happening. So, let us give it an anti-clockwise rotation. Let it get cooled down because the plate was hot. Right now, we have now changed the direction of the temperature. Now, the temperature was flowing from bottom to top. Now, the temperature is going to go from top to bottom, top plate to the bottom plate. While it is just getting cooled down, one interesting thing about the Stirling engine is that it does not eject anything, unlike steam engine or gas engine and all that. The gas is contained in a particular space, and it is soundless. However, it does not give enough power, because in order to get the power that is required for, let us say, running a car or other bigger machines, it will require much larger system, much larger engine, and therefore, but people are trying to make it better. And another interesting thing is that wherever there is a temperature difference, for example, these computers generate a huge heat and all, right. So, let us say one can manipulate and put a Stirling engine to take the ejected heat out of these computers and throw it outside in a cold environment, let us say Norway or somewhere wherever the temperature is very cold, but inside it is heated up. There one can use that, and then you can use Stirling engine to extract more this thing from extract work out of that. So, now let us try that anti-clockwise direction, and you can see it is working in the anti-clockwise direction slowly, because the temperature difference is not that great. Earlier the temperature difference was 24 to 70, which was almost 46-degree difference, but here the difference is 24 to 0, which is like 24-degree difference. So, larger the difference is, you have seen the efficiency is going to be more and more, depending on the difference of TL and TH, the efficiency is going to change. Now, you see from your direction, when the piston is away from you, it is now anti-clockwise rotation is happening, whereas in the other case it was happening in a clockwise direction. So, just one more important point that I would like to make is that in the Stirling engine we saw that heat transfer from low to high moves the wheel. That means heat gives rise to work, but and eventually what is going to happen is that the temperature difference is going to decrease between the two plates. and efficiency is going to reduce slowly, because heat is constantly taking in and leaking out from that. Unless we maintain the temperature difference, is going to come to the same. Now, I have put it for a long time on top of ice. I am just going to show you the temperature. 24.9, 25.0, very similar temperature difference, and we saw that will stop. In the same manner in which we have put the heat and did the work, we can do the other way around. We can actually do the work and create the temperature difference. It is just opposite of work to heat and heat to work. As we know that, right, the energy is conserved. So, right now if we do that for a long time, I do not know how long, we have to really try. If we do that for a long time, this is going to create a temperature difference. So, right now, can you tell me like whether the top plate will be hotter or the bottom plate will be hotter? I am moving it in the direction where it is a clockwise manner. Yeah. So, if you do that, the bottom plate is going to be hotter, because that the flow of heat has to be from here to here in order for it to rotate in a clockwise manner, but probably we have to do for a long time. Yeah. So, as I said that changing the hot and cold side will lead to the cycle moving in 1 4 3 2, which is currently happening now. Without heavy wheel, the momentum will not be enough to go through the contraction phase. So, there is an expansion, there is contraction. Initial momentum is required. So, if you just put it on top of hot plate or cold plate, if you do not touch the engine, it will not work. At least you need to give an initial momentum, because the situation is like that, you are not, the system is not always kept at 3, such that in the first step itself you will get the expansion to 4. Typically it is somewhere in the middle. So, therefore, you have to give up it push to at least cross one cycle once. Once it crosses one cycle, then for the subsequent cycles the work that or the heat that is taken in between 3 and 4 will be enough for it to go over the cycle. And without the regenerator, as I said, that efficiency will be less. So, this particular engine has lower efficiency compared to the ideal Stirling engine, which has of course, this has lower efficiency for many other reasons, because it is a realistic one. It has frictions and it has many other things. It does not have an ideal gas and ideal expansion and all that. So, a typical engine, a realistic engines will always have lower efficiency than the ideal engine. But the interesting thing is that while Carnot designed this particular highest efficiency engines, Stirling already had made or designed an engine which works, and that has the same efficiency as that of the Carnot engine.